Let us start lecture 33, and today's topic will be condensed solution, and that to ideal solution. And then we will try to see the graphical presentation of three quantities, what is del Hmix, del Smix and del Gmix. These three quantities will be important to decide the equilibrium condition when there will be two phases or rather multiple phases in a system. Okay. And in the last few lectures what we have discussed to get expression for all three mixing quantities, and those and in case of binary system, let us say A and B, these are the two components, and that time we can actually express those three quantities in the following fashion. So, if we try to see del H mix for ideal solution, and that time we have taken A and B, these are the two components we are taking. Pressure and temperature we are keeping fixed, and this is, let us say, closed system. And here what we are saying, we are not actually having any chemical reaction. That means we have different compositions, but chemical reactions are not taking place. Now, del H, and also we have seen that initially we have considered Na and Nb moles which are mixed. Na is the number of mole for A and Nb is the number of mole for B, but now gradually we will shift to 1 mole of solution, and that time we will take a little change in that. We take Na and Nb, these are the number of atoms if we consider mixing of two metals, let us say. Mixing of two metals when we try to see, and these are the number of atoms, and these atoms, number of atoms are taken in such a fashion that Na plus Nb equal to Nv, which is nothing but Avogadro number. Fine. It suggests that we are actually making 1 mole of solution, and if we try to understand the mole fraction, that mole fraction can also be written as Xa as well as Xb, and that time we can actually divide the number of atoms with the total atom. Since it is 1 mole, we can get the mole fraction. In fact, this can be actually related to this. Fine. Such a fashion that, let us say, if we take Na and Nb number of moles, and then if we add them together, that time it will lead to 1 mole. So, still we will get Xa and Xb, and Xa and Xb if we add them together would lead to 1. Okay. So, those are the conditions we are taken. So, these are the conditions, and this ideal solution, it is in condensed condition. So, that means either solid or liquid solution we are considering. Okay. Either solid or liquid, these are the so that time we have found out that del, these are the condition what we have taken, and that gives me following expression: del H mix equal to 0, del S mix equal to minus R Xa ln Xa plus Xb ln Xb, and then we get del G mix equal to del H mix minus T del S mix that yields me R T XA XA ln XA plus R T XB ln XB. Okay. So, these are the quantities we have to see graphically. Okay. So, first let us see how this one operates on a graphical plot. So, if we take let us say pure, this is A and this is B, and let us say x b we had is this way, and here x b equal to 1, here x a equal to 1. So, that means both the sides are pure, and if I try to find out del H mix equal to 0. So, this will actually lie on this line, considering that these two values are taken as 0, fine. So, and this is the axis for del H mix, fine. Now, if I try to plot this one, so if I try to plot del S mix, this is x b, B side, A side, these are pure condition, and now since this particular plot would be like this, the symmetric curve, this is the kind of plot you will get. This is let us say del S mix, and this is 0, this is 0, and it will be always positive. Since x p and x a both are fractions and there is a negative sign here. So, in case of alloy, if I try to consider a solution, and or since two metals are added, we are actually making an alloy. So, we are making an alloy. Which could be liquid, solid or liquid. In fact, these alloy is homogeneous as well as this can be considered as solution of two metals. So, now in this case, if we try to consider homogeneous solution, and we are also thinking of ideal solution, that means A and B are miscible over one. So, less than 1. So, in this entire composition range, of course, pure metal would be remaining pure metal. So, within this composition range, entire range, it will be A and B will be completely miscible. So, that is the condition of ideal solution. Okay. Now, this also can be considered as a random mixing. Random mixing. In fact, when we try to prove this del S mix with the expression of this, so del S mix can be written as S solution minus SA minus SB, if you recall. So, this goes to K ln omega solution, this W solution. So, in fact, these two quantities will be 0. So, now from here this particular thing we have taken as no preferential sites, rather every A and B both are completely miscible over the entire composition range, and those are randomly mixing. No specific preference for A or A to A or B to B or A to B. Now, that time this is at the midpoint, x b equal to 0.5, then only you get this particular point. You can prove that by, since it is actually having a plateau, you take equal to 0. If you do that, you will get xb equal to 0.5. So, at that composition you get the peak. Now, once we have plotted these two, let us see how del Gmix is plotted over this two composition range. And here we are taking binary solution. So, if I try to look at so this is again pure B, x b equal to 1, this is A, x a equal to 1 and x b varies this way. Now, these are 2 points which are 0 0. So, now if I try to look at del Gmix equal to minus T del Smix, since del Hmix equal to 0. So, this particular del Smix quantity, you multiply the temperature where you are actually having the solution, and then it will be varying on the negative side. So, the plot would be like this. So, this is minus T del Smix, and if I try to see del Smix would be like this. So, now this goes to minus del Smix, and minus del Smix is nothing but delta Gmix. So, this is at a particular temperature T. Now, if I change the temperature, del Smix will not change, because del Smix quantity does not have any temperature term. If you see this particular expression, no temperature term, that will not change with the temperature. Now, if I change keeping the pressure constant, if I change the temperature, this del Smix would remain same. The only change would be in the minus T del Smix. So, if we reduce temperature, so that time it will go up, this particular quantity go up. This is, let us say, minus T1 del Smix, and this is T, and here the relation between T and T1 should be T1 is less than T. Now, if I increase the temperature, then it will go down, it will further go down. Okay. It will further go down. Let us say this is minus T2 del Smix. Okay. So, the relation between this would be fine, and every time this is delta Gmix at, and this is equal to delta Gmix at T1 and here at T, okay, like that. So, now correspondingly you see that the curve is symmetrically moving up and down depending on increase in temperature or decrease in temperature. But in case of ideal solution, del Gmix is nothing but minus T del Smix, and in fact this delta Gmix can be actually written as x a delta G m a plus x b delta G bar m b. We can write that, and this is for a particular solution or particular alloy. Let us say we are taking a solid solution. So, bracket we can put S. So, everywhere this is for S, remember that, and even this composition also for S, that means solid solution. Okay. S is solid solution, and if we try to put if I try to calculate liquid solution, then it will be for the liquid. Okay. Every quantity would be for the liquid. Please remember this particular aspect. Whenever you write this expression, it has to be for a particular homogeneous solution. You cannot mix X A and X B for solid and liquid, or delta G A bar M as well as delta G B bar M for solid liquid. So, one quantity is for solid, another quantity is for liquid. You cannot do that. Okay? It has to be for the same solution. Once you write that, we can actually get the expression for delta G A bar M as well as delta G B bar M. These two quantities we can actually find out, and in fact this is nothing but RT ln X A and this is nothing but RT ln X B, but we can actually calculate it if we know simply the del Gmix quantity. So, in fact, if you recall that Gm, which was the solution free energy, this is for free energy for solution. So, that can be written as X A G A bar plus X B G B bar. G A bar and G B bar are basically partial molar quantity for A in the solution. Similarly, G B bar is nothing but partial molar free energy for the B component in the solution. So, that time if you recall, we found out an expression, this one equal to G M plus X B this, and G B bar equal to G M plus X A these two quantities we have found, okay, the partial molar quantity. Similar route we can actually find out this one as well as this one. Why we want to do that? Because we want to also reflect it over the this particular graphical plot. What is basically this quantity? We need to find out that this quantity, how it actually is placed on this particular plot, how it is placed. We want to find that. Okay. But before that, first let us see how we get this, whether we can get similar expression like this for these two quantities. Fine. So, in order to do that, so we can go like this. So, delta G mix equal to X A delta G A bar M plus X B delta G bar M B. Okay. Then this is equation 1, let us say. First let me do this. Okay. Now, if you recall Gibbs-Duhem equation, one equation says that delta G equal to G A bar d x A plus G B bar d x B, and another expression says this one equal to X A d G bar A and then X B. Okay. So, now this expression can also be taken, these two formula can also be taken here, considered here. So, now considering this second one, this particular expression, we can write x a d delta g a bar m plus x b d delta g bar m b should be 0. So, we are left with fine, and since it is a binary, so x a plus x b equal to 1, and hence we can write dxa equal to minus dxb. So, now so replacing this one with minus dxa, so then I can write delta g bar m b. Okay. So, once we write that, we can multiply both side with x b. So, multiplying x b. Okay. Now, this equation, let us say 2. Now, if I add equation 1 and 2, so that yields me x a g a bar m plus x b, sorry, it should be delta g b plus x b delta g m bar a minus x b delta g bar m b. So, you see these two quantities should get cancelled. Now, you are left with this quantity and this quantity. So, I can write x a plus x b delta g bar m a. So, hence this is nothing but 1. So, delta g bar m a is nothing but delta g mix plus x b dxa. Okay. So, now you see we are getting one of those expression. So, if we know delta g mix expression, we can easily calculate the two partial quantities. Fine. Similar way one can find out the other one, where only thing that has to be done here. So, from here if I try to find out delta g b m, so in order to find that, we will replace x dxa with minus dxb. So, the same expression we can replace here. Okay. So, if I replace that, we get delta g mix equal to delta minus delta g bar m a plus delta g bar m b. Okay. So, now then we multiply with x a. So, this becomes equation 3. So, now if I add up equation 1 plus equation 3, I will get I think we missed this. Fine, this one. Okay. So, should be equal to x a delta g. Let me just write this expression. So, these two get cancelled. Now, we have this. So, then we can write x a plus x b delta g bar m b equal to delta g mix plus x a So, you see this is equal to 1. So, we get okay. So, this is equation, let us say 4 and this is 5. So, 4 and 5 equation we will now try to see how they are spaced on that free energy versus delta G mix plot. Okay. So, that we will do in the next lecture. So, till then, thank you very much.